Hi everyone, welcome to Homework 2.15. Today we are looking at inverse functions, which basically means that instead of solving for one variable, we're solving for the other one. And this can only be true if the other variable can be a function of the original solution. So let's take a look at Noah's cousin is exactly 7 years younger than Noah. So in my head, I'm already figuring out that the cousin is Noah's age minus 7. You may have in your head said, well, the cousin's age plus 7 equals Noah's age. That's also fine. We're going to see that down below. So it says write a function that defines the cousin's age as a function of Noah's age. So if we're writing the cousin's age as a function of Noah's age, function of means that here Noah's age is the input. So that means I'm looking at this equation. The cousin's age equals Noah's age minus 7. You could also write this as f of n equals n minus 7. Remember, we talked about this variable representing the cousin's age. This is the same as that function output is representing the cousin's age, or if you wanted c of n or something. And then the inverse of the function that we wrote would be this one here, where we're looking at Noah's age. Now we're writing this as a function of the cousin's age. So the cousin's age is the input, or f of n in our function notation, or sorry, f of c. f of c, because that's our input, equals c plus 7. Noah's cousin is exactly 7 years younger than Noah. Let m represent Noah's age, cousin's age in months, and n represent Noah's age in years. So now we're looking at the cousin's age and Noah's age, but we're looking at it in months versus years. So if Noah's 15 years old, how old is his cousin in months? Well, if he's 15 years old and his cousin is 7 years younger, that means his cousin is 8. And so then 8 times 12 gives us 96. So his cousin is 96 months old. When Noah's cousin is 132 months old, how old is Noah in years? So 132 divided by 12 months gives us 11. So 11 is Noah's cousin's age, but then to get to Noah's age, we need to add that 7 years. So now Noah is 18 years and his cousin is 11 years. So it says write a function that gives the age of Noah's cousin in months as a function of Noah's age. So in this case, m is the cousin's age in months. So m equals the Noah's age is Noah is 7 years older, so Noah minus 7 gives us the cousin's age, but now we need to multiply that whole thing by 12. You can leave it like this, or you can write it as m equals 12n minus 84. That would be fine as well if you want to distribute that, but it should be equivalent to 12 times n minus 7. All right, it says write the inverse of the function you wrote. So now in this case, I'm solving for n. So what I'm going to do here is m equals n minus 7 times 12. I'm going to divide both sides by 12 because I want to get, in this case, n by itself. So now I have m over 12 equals n minus 7. And then I can add 7 to both sides. And so we'll get n equals m over 12 plus 7 as this now is the function of the cousin's age in months gives us the output of Noah's age in years. And that's what we did here, right? We divided the months by 12 and then we added 7 to get Noah's age. All right, this next one, each equation represents a function. For each, find the inverse function. So here what we're doing is we're just solving. This is the input in this situation, but we want to solve now to make this the output and this the input. So I'm going to subtract 3 from both sides, and w equals c minus 3. These are very similar to literal equations that we looked at before when you have an equation and someone tells you to solve for the variable that's in the equation. So here I would want to solve for x, so I'm going to add 2 to both sides, and we get x equals y plus 2. Here, the inverse would be division, so I'm going to divide, and x equals y divided by 5. Here, the inverse is the multiplication, so I'm going to multiply both sides, and I get d equals 7w. All right, the number of years y is a function of the number of months m. So this means this is the input. I'm going to label that for myself so I remember it. The number of months m is also a function of the number of years. So we can also say the opposite. So write two equations, one to represent each function. So we can say years equals the number of months divided by 12, or we can say months equals 12 times the number of years. So you can check to make sure that that's accurate, right? If I said 2 years, I would plug 2 in here and that would give me 24 months. That's true. We know that 2 years is 24 months. If I were to plug in the months here, let's say I had 12 months. 12 divided by 12 is 1. That gives me 1 year. If I were to plug in 18, it would give me a year and a half, right? And so you can check to make sure it works and makes sense by plugging in numbers for months and years. And these are inverses because when we solve for the other variable, we do an inverse operation. And for each input, there is one output in both situations, right? So if I plug in 1 year here, the only possible output there is 12 months. I can't plug in 1 year and have 12 months and 24 months, right? There aren't two outputs. So that's a function and that works. And then likewise here, if I plug in 12 months, the only possible output is 1 year. All right, sketch a graph to represent each quantity described as a function of time. Be sure to label the vertical axis. All right, so this is just sketching, right? So it's not going to be 100% accurate. You're just trying to create a depiction of this. All right, and so it says the height of your feet above ground while swinging on the playground. So the time is the input here. Here is the height of feet above ground. Now, depending on how tall you are, your feet may or may not start on the ground, right? Like if I'm pretty short, but on a swing, my feet touch the ground now as an adult, right? And so this would, my feet might start on the ground, right? As I'm like kind of running across the ground to push myself up. And as I swing up, my feet are going to lift off the ground. As I swing back down, they're going to come back to the ground and so forth. Now, if I were a child, let me do it in a different color, my feet, like my daughter's feet, don't touch the ground, right? So she's going to come up and then her feet are going to come back down. Her feet are never going to touch the ground, right? So you could have several different graphs that represent this, but you should have a wave because as you swing up, your feet get further away from the ground. And as you swing back down, they get closer to the ground, then further up, and then back down, okay? All right, a slide. The height of your shoes above ground. All right, so that's our y-axis, height of shoes above ground. As you walk to the slide, so as I walk to the slide, my feet are on the ground. And then I go up the ladder. Each foot steps up on the ladder. And then we go down the slide. My feet come up and swing around and go down the slide. Back down to the ground. A merry-go-round. Your distance from the center. So distance from center. Now, if this is the center of the merry-go-round, right? And then this is the outside of the merry-go-round. And I am here. And I'm riding around. My distance from the center is going to stay the same the entire time because it's going around in a circle, right? And so in this case, my distance, let's say I'm like 5 feet from the center of the merry-go-round, is going to stay at 5 feet the whole time as I move around. My distance relative to other things is changing, but my distance to the center is going to be the same. So this should be, that's not the best straight line, but that's a straight line. All right, and then the merry-go-round again, this is the distance from your friend. So when I said relative to something else, so let's say that my friend is standing next to the merry-go-round here, right? And so as I go around, I'm coming closer to my friend and then moving further away, closer, further away, closer, further away, right? And so I'm not right next to my friend to start with, I'm away from my friend, and I'm going to be moving further, closer, etc. So that graph should look very similar to this one in that you're distance is changing over the course of time. All right, Lynn charges $5.50 per hour to babysit. The amount of money earned in dollars is a function of the number of hours that she babysits. Which of the following inputs is impossible for this function? Well, the only one that's negative is -1, because I can't babysit for -1 hours, right? So 2, 5, 8, they're all possible. 8 might be a bit much, but maybe she's really lucky and she needs to up her rate a little bit though, especially if she lives in DC. Okay, let's look down here. We have a review of our piecewise functions, just so you don't forget them. The instructions for cooking a steak with a pressure cooker can be represented with a set of rules where X represents the weight. So this is the weight of the steak, and this is our cooking time. Describe the instructions in words they can be followed by something using the pressure cooker. So I'm going to start this off, and then I want you to continue it. So if the steak is greater than or equal to 8 ounces and less than or equal to 12 ounces, cook for 7 minutes. Then notice the rest of these are going up by 1-minute increments. So every minute that is added, then what do we do for our time? Okay, or not every minute, every ounce that is added, what do we do for adding time here? Okay, now it says graph function f. So let's start between 8 and 12 ounces. So that would be here and here. And it's including, because it's greater than or equal to and less than or equal to, it is 7 minutes. So I'm going to go up to my 7-minute mark, fill in my bubbles, because it's including, and draw my line in between. All right, so any ounce of steak that is between this area in the X value is going to be for 7 minutes. Then looking at 12 ounces, it goes up a minute. And until we get to 13 ounces, we're going to be at 8 minutes. Then from 13 to 14, we're going to be at 9 minutes. From 14 to 15, we're going to be at 10 minutes. And then from 15, not including 15, right, but through 16, we're going to be at 11 minutes. So this just shows you that different cooking times are going to be required for different ounces of steak. All right, moving on, the absolute value function q of x equals the absolute value of x gives the distance from 0 to the point on the number line, right? So again, thinking about your number line, -1 is 1 away, 1 is also 1 away, which is why our absolute value is always going to be positive. It can also be defined using this function, which you saw in your homework yesterday. Determine if each point is on the graph of Q. For each point, if you believe it is not on the graph, change the output coordinate. So in an absolute value function, we should always have positive y values, right? So -3, 3 would work because that would be over here and up here, and we know we need to have our V shape, right? So this is fine. 0, 0 is fine. That would be our vertex. -5, -5, so that would be over here. That is not on our graph, and if we were to change this, we would need to make this -5, 5. -72 and +72, that would be over here and then all the way up there as part of our V. That is fine because this is positive. And then this does not work because we have this -4/5. Now this could either be -4/5, 4/5, or this could be 4/5, 4/5. Both would be fine because, as we discussed, it's symmetrical on both sides. All right, that is it for your homework today. Let me go back really quickly and look at this part right here in case you didn't get to this part in class. So all you're doing is matching these equations with these graphs down here. What I would recommend that you do is looking for the vertex and label the vertex first. So here the vertex is -1, -3. This helps me to write my equation then because I know I'm moving to the left, so I'm doing x plus 1 in the parentheses, and then I'm moving down, so outside of the parentheses, I'm subtracting 3. And you can test this by plugging in your vertex. If I plug in -1 plus 1, I get 0, minus 3 equals -3. And if as long as that equals, when you plug in your vertex, you know you've done it correctly. So here my vertex is 3, 1. So here I should have y equals, now I move to the right, so I'm going to subtract inside, so x minus 3, and then I moved up 1, so I'm adding 1 outside of my absolute value modulus. All right, here we have 3, -1, and so y equals x minus 3, right, because our x value is the same as this one here, and then I'm moving down 1, so minus 1. And again, if you were to plug in your x and y values, 3 minus 3 equals, 3 minus 3 is 0, 0 minus 1 is -1, it works out. So if you plug your vertex into the equation that you created, it should be true. If it's not true, you made a mistake. All right, -1, 3. Here I move to the left, so inside my modulus, I'm going to add 1 because I moved 1 to the left. And then I moved up, so I'm also going to add 3 outside of the modulus. All right, so those are the first 4 answers for that classwork piece. You can go ahead and continue to work on this piece right here. All right, that's it. You don't need to remember, if you didn't fully get to this part, it's okay if you didn't finish it. And if you have any questions about the homework, please reach out. Happy homeworking. Oh, code word. Code word today is chaos. Chaos, and extra credit if you spell it correctly.